Uh, well, thank you all for coming here and giving me the opportunity to share mine and my lab's recent efforts in method development in the lambda dynamic space. And so I'm going to be talking about superimposing ligands with ligand overlay using lambda dynamics with bias updated Gibbs sampling. And we're doing our method development. The place that we are doing a lot of this development is in free energy calculations and small molecule drug discovery. We're both using, there's multiple options when you're doing free energy calculations. Obviously, you have your absolute binding free energy and also relative binding free energy calculations. Typically, absolute binding free energy calculations are more computationally expensive and slower to converge, but there's been a lot of developments in that space, and that's very exciting. But our method development is going to be in the relative binding free energy calculations, and we like to use those because that enables us to make faster and enable thousands of free energy predictions in a relatively short amount of time, and prioritize our top ligand candidates for further studies and help experimentalists focus their efforts on the most promising compounds. We're in our lab is in a biochemistry department, and so we work with a lot of experimentalists, and when we give them our free energy predictions, one of the things that they always want with those predictions is to look at why this is happening within these simulations. And so making sure that we have those atomistic insights into the dynamic processes really helps, and we can enable visualization of these trajectories for interpreting experimental phenomena and explaining observed behaviors and validating those computational predictions. And if any of you went to one of my lab mates, Monica's poster yesterday, you can see how much information you can get from these simulations and how much structural data that you can show to these experimentalists when they want to see it. And we're doing method development, and our goals with method development is making sure that we have we're improving efficiency on previous methods, as well as either maintaining or bettering accuracy and maintaining those atomistic insights, as well as making sure they're transferable between lots and lots of different biological systems. And so traditional methods in this area, such as FEP or TI, utilize many intermediate alchemical states to bridge the endpoints of interest. And each of these states, is run as an independent simulation. I think I only have 4 of them up here, but typically we're looking for a small molecule, more like 11 lambda windows, and each of those is going to be a separate simulation. And then if we start using expanded ensemble methods, as we've heard about in earlier talks today, even the simulation, it allows us to sample multiple thermodynamic states in a single simulation. And there's been some very interesting developments in lambda dynamics and envelope distribution sampling, and obviously even more. And just to kind of break down that efficiency, I was going to show sort of how it compares to a typical TI simulation. And so if you're just doing a pairwise calculation, and again, I'm only showing 4 lines, but that's just for illustrative purposes. We're looking at 11 lambda windows, and that's 11 simulations and 55 nanoseconds of total simulation time. We just want to add 2 more perturbations. Now we're looking at 33 separate simulations and 165 nanoseconds of total simulation time. And just adding 2 more, it gets even worse, and you're getting 55 separate simulations with 275 nanoseconds of total simulation time. And so if we move on to sort of some expanded ensemble methods, we can sample a lot of these states in a single simulation. And so if you're looking at lambda dynamics, we can sample and explore all of these states in about 15 nanoseconds, although not 15 nanoseconds total, because there's going to be burn-in time for bias determination. But this is really advantageous for virtual screens and drug discovery, because it enables us to simulate the sampling of all those ligands in the same simulation and reduces the number of independent simulations and improves the sampling efficiency and convergence. But to get down to just the 15 nanoseconds total, I'm going to be talking about lambda dynamics with bias updated Gibbs sampling, where we're no longer going to need that burn-in time ahead of that 15 nanoseconds. And now you're exploring all 5 of those states within a single simulation. And we're going to be, and this is different from previous lambda dynamics methods, is we're going to be using discrete lambda states, which are now going to be defined along the connective edges there. And to get into more detail about lambda dynamics with bias updated Gibbs sampling, or LaDyBUGS as we like to call it, it's going to be following a Gibbs sampling, which is a Markov chain Monte Carlo algorithm, which samples a conditional joint distribution. And we're going to have alchemical states lambda and atomic coordinates. And just like with thermodynamic integration, or FEP, we're going to be using discrete intermediate lambda windows to connect those ligand end states. And so the first thing we have to do when we're setting up our lambda dynamic simulation is we have to initialize the system. And so to encourage the sampling of all the states without that burn-in time for bias identification, we use an aggressive scalar bias on each lambda state to start with. And then to set our initial coordinates, we use our initial minimized structure, and an initial lambda state is chosen. And then we can start our Gibbs sampling step. And that's going to involve running a molecular dynamic simulation at a fixed lambda for a set amount of time. And once that simulation ends, we're going to calculate the potential energy at the new set of atomic coordinates for each lambda state. And those results are going to be normalized into a Boltzmann distribution. And then we use a pseudo-random number generator to choose the next lambda state based on the probability. And that iterates until we've explored all of those lambda states. Also, we start with a very aggressive bias at the beginning of the simulation for each lambda state, but at the end of each Gibbs sampling step, the bias is updated for each state. And that's done by calculating the intermediate free energy results, which are saved for all lambda states and sampled at all atomic coordinates. And this bias is refined throughout the simulation to allow easy exploration of all states. Our objective when we're doing this was to test the accuracy of the method against both experimental benchmarks as well as previous methods. We wanted to show comparable accuracy and superior efficiency and transferability between biological systems. So to show that transferability, we tested this method in 5 model systems with 45 ligands. And these substituents are also going to be very different. Some of them are going to be, just like a single heavy atom change. And, some of them are going to be whole aromatic rings, and, and some of them are going to change, 10 to 12 heavy atoms in a single perturbation. And I would also like to point out that these are all going to be single site perturbations as well. And we were testing in our LaDyBUGS simulation, we wanted to run things in groups of 5 to 7. And so in some of these that have more than that, we broke them up into 2 groups. And in each of them, we show the core in the box as well as the reference ligand. And in the case of 2 groups, the reference ligand is going to be used in both simulations. And so to test this, we're gonna compare this to TI as well as experimental results. And we wanted to keep all conditions the same for both simulations. So we used OpenMM and the Charm 36 force field for all of our protein atoms, and our small molecule ligand atoms were parameterized in ParamChem and CGenFF. And to look at our experimental benchmarks, we have our TI on the right and our LaDyBUGS simulation on the left. We ran our TI using a star map strategy. Each transformation between the hub and the surrounding state is computed over 11 lambda windows. On the left there, we have our LaDyBUGS simulation. Again, that was 5 to 7 ligand perturbations in each simulation. And it looks like we have 5 nanoseconds per window for TI and 15 for LaDyBUGS, but this is just 15 nanoseconds total, and this is per window. But overall, we had pretty good experimental agreement with both. Our TI, our LaDyBUGS had a slightly lower RMSE and a slightly better Kendall tau, with 1 being perfect, and but both right around 1 kcal per mole. And so we were happy with this, but we also wanted to compare LaDyBUGS directly to TI. And there we now graph them together. So we have TI on the x-axis and LaDyBUGS on the y-axis. And you can see they compare, they agree with each other quite well. We have an RMSE of less than half a kcal per mole. We have a Kendall tau of 0.86. But the major difference here between LaDyBUGS and TI is going to be our efficiency, our sampling efficiency. which, when we were looking at all of our data, we did a total of 360 nanoseconds of sampling for LaDyBUGS to get these results, while we needed 12,705 nanoseconds to get the same results for TI bar. And so our efficiency gain there was 35-fold over the 5 systems. But to test to see if that was the best efficiency gain we could get, we tried it with LaDyBUGS when we only ran it for 5 nanoseconds total and compared the data. And you can see the RMSE and the Kendall tau are actually quite similar to when we ran LaDyBUGS for 15 seconds and compared it to TI. And now in this case, we have all of our data has a, for LaDyBUGS has 120 nanoseconds, and for TI, we're looking at 12,705 nanoseconds for an efficiency gain of over 100. And then the other thing we wanted to do was test, if we ran our TI for longer, to see how well that will also compare to our LaDyBUGS data. So now we're doing 15 nanosecond lambda windows for TI and 15 nanoseconds total for LaDyBUGS. And again, the RMSE does go down, and it's now 0.35, and our Kendall tau goes up a little bit. But the major thing was that the uncertainties in our TI simulation on PFKFB3 are also now very similar to our LaDyBUGS uncertainties. And so looking at all of our data again, we have now an efficiency gain of 113. One of the things you guys may or may not have been paying attention to is that we've had to have different levels of sampling for some of our systems for thermodynamic integration. And the reason for that is because in our LaDyBUGS simulation, we're scaling our dihedrals by lambda. And that's allowing it to explore multiple conformations of the alchemical group in the binding pocket. And in our TI simulations, we weren't able to capture that. And so we had to start with a different structure initially in order to capture that. And so that increased some of the sampling in some of our simulations. And just to show you what it sort of looks like in our PFKFB3 simulation, we had to flip this ring in our TI simulations in order to sort of capture that change in the binding pocket and get it to agree with our experimental benchmarks as well as our LaDyBUGS predictions. And this is what the dihedral angle looks like throughout a single simulation. And you can see we've got multiple conformations of that alchemical group during our LaDyBUGS simulation. And in our TI simulation, we're only going to be able to capture one. So we had to run separate simulation to capture that as well. But overall, we were very happy with our results, across our 5 benchmark systems. LaDyBUGS showed comparable or better accuracy than the classical method, while being 18 to 200-fold more efficient. But we didn't stop our method development here, although we did publish a paper here. But we were looking at how we could make the setup and make this more efficient and more easy to use for a larger group of people. And one of the ways we thought that there was sort of a bottleneck at the very start was setting up our system. And there's a lot of reasons for that. But when we're setting up our ligands, one of the major things is that we have to partition the partial atomic charges in order to create a functional model. And what we've done typically in lambda dynamic simulations is we use a hybrid multiple topology model. And this hybrid multiple topology model shares characteristics of both single topology for the common core, while they have a dual topology for the alchemical groups. This offset is just for illustrative purposes. But the problem that many of you are probably thinking with that method is that our common core is going to have a certain charge. And for our reference ligand, it's going to be the same charge because this is going to be a neutral ligand. But when you're sticking something new onto that common core, this is going to have a different partial charge. So what you have to do when you're running these simulations with a hybrid multiple topology is you have to change that charge so that, you kind of average it all out and change it so that it's all of the ligands that are tested within the system are going to be neutral. And then you have to correct for that at the end of the simulation. And this is a bit of a long process. Sometimes it it takes more simulations just to correct this charge. And it can also create error when you're partitioning those atomic charges. And just to illustrate that, I'm showing some average deviations in the relative free energy of hydration going from our force field, our CGNFF charges, to the hybrid multiple topology. And you can see, in some of these ligands, and even though there's just a single change, it's changing the free energy of hydration by by almost 2 kcals per mole. I mean, in some of these, the change is actually relatively minor, but in others of these, it can actually go up much higher and at almost 4 kcals per mole. And setting up and doing these back corrections causes extra simulations, and it can be time consuming. And renormalizing these charges can produce error, and correcting them can create potential artifacts in your free energy results. And so we wanted to avoid all of this. And so all of this effort can be completely avoided using the ligand overlay topology model that I'm about to show. And it also will allow the use of different force fields because you can use whatever charges you want. So the ligand overlay model differs from the hybrid topology model because the perturbation occurs between whole ligands rather than side chains. So it's going to be, rather than a hybrid topology model, it's going to be more of a dual topology model. And one of the things that we have to do in order to make sure that this is possible is that if we're perturbating between entire ligands, some of them are going to be off and not interacting with the environment. And when they're off and not interacting with the environment, the problem would be that they could just float off out of the binding pocket and into space and give us horrible free energy results. So what we decided to do was using the maximum common substructure and the constrained atoms utility and charm, we put a harmonic restraint between the pairs of atoms on the maximum common substructure. And again, this is just, the offset is just so that you guys can see it, but this would be like right on top of each other. And this is nice because only one ligand is going to be on and interacting with the environment at a time. But because the maximum common substructure is paired together, none of those ligands are going to be floating off into water or space or through the protein atoms when they're not interacting with the environment. And then when they turn back on, they can adopt the configurations that they need during the simulation. And then some other advantages to using ligand overlay with Lambda Dynamics and LaDyBUGS is that it now makes all changes to the ligand scaffold a single site transformation, which simplifies LaDyBUG setup because it doesn't matter if you're putting a group here or here. If you're perturbating through all the ligands, it's just going to be a single site change, so you don't have to worry about where you're putting any of the perturbations now. It completely avoids all the partitioning of atomic charges and any associated error with that. And it allows the easy use of other force fields because now you're, instead of having to correct for any changes in charges, and because these are perturbating between whole ligands, you can parameterize them in whatever you want. And so this setup method will be force field agnostic. But to test to make sure that putting this harmonic restraint on the ligands isn't going to be causing any issues or artifacts that we don't know about, we did kind of a sanity check and a control experiment where we did a series of symmetric perturbations, which are very nice because the answer by definition should be 0, and showing that it's 0 can rule out some of those artifacts being controlled by ligand overlay. And so we use LaDyBUGS to compute the free energy differences for a set of pairwise and multiple symmetric perturbations performed with ligand overlay, and we used one ligand per group that I showed earlier. And you can see these are all very close to 0 within our uncertainties. And then when we just perturb between multiple copies of the same ligand in the same simulation, again, we got very close to 0 within our statistical uncertainties. And so we were very happy with that. And we decided to move on and compare this to our hybrid multiple topology simulation. And what we got was, happily, it compared, it was very, very close, like an MUE of 0.32 and a Pearson R of almost 1. So the results that we were getting from this were very, very similar to the hybrid multiple topology. And this is very good to know because, as we showed earlier with the hybrid multiple topology, we were able to get very good agreement with experimental results as well as with TI. And so showing that, we're able to retain those same predictions with our ligand overlay suggests that we're simplifying the setup without changing the free energy results themselves. And this is also nice because I know there's a couple of things that we tested that I'm not going to show during this presentation. We also retain that alternate, we're able to retain the ability to look at some of those alternate binding poses because we're still scaling our dihedrals by lambda. And also the harmonic restraint isn't affecting the internal dihedrals of the ligand. It's still able to move around and change during the simulation as needed. But overall, we were really happy with this, and we think this is going to be helpful for looking at future drug discovery projects. And so just some key takeaways I wanted to go over was that LaDyBUGS maintained accuracy while increasing the speed and efficiency of those binding predictions. We successfully benchmarked it in 5 systems with diverse sizes and substituents, so showing that it was transferable between multiple biological systems. We had a very high agreement with thermodynamic integration while being 18 to 200 times fold more efficient. And we were able to capture alternate alchemical binding conformations. With ligand overlay, we increased the setup efficiency while maintaining our accuracy. We avoided the time-consuming partitioning of atomic charges and simplified the setup. We minimized the number of lambda states by avoiding multi-site perturbations. And we retained the alternative binding poses found in our hybrid multiple topology model. So some future directions that we want to take this project. We want to apply the method with other force fields. I said it was force field agnostic, so testing it in other force fields would be a good thing. And we want to utilize ligand overlay with LaDyBUGS in a prospective drug discovery projects. And so with that, I want to thank my lab, Dr. Jonah Vilcek, who's here, as well as Monica Barron, who just graduated, and our collaborators, and of course our funding sources and the IU High Performance Computing Center. And thank you all for your time.
Thank you for the talk, Michael. We have time for questions. For one question, we are already running out.
Yeah. So what we've just go back to this. So you're saying so the ligand overlay in our core when it's off. Yeah. Right. Yeah, I mean, it would in that case. So a lot of these are small molecules, and so a lot of the motion that's happening during the simulation in that like maximum common substructure area is going to be very similar between the different ligands, and so it doesn't really seem to affect the free energy results too much. And I think that's why you're seeing like such a good agreement with hybrid multiple topology and with our ligand overlay. Yeah.
Thank you.
Yep.
Let's thank Michael again. We have 20 minutes break from now. Thank you.